All right. The only announcement I want to share with you is that your next assignment is due on Wednesday. Watershed modeling number 2. So that assignment's been posted on Blackboard for a while. And we're going to continue working on WMS today. So far, you've learned how to do the rational method, national streamflow statistics, TR55. And then on Friday, the demo was meant to illustrate the process you go through in order to automatically calculate the curve number. And we're going to repeat that part of it today, and then also go a bit further into a modeling, a watershed modeling technique called HEC-1. So any questions before we get started? All right, so if not, the file that you need, that text file that has the curve number table, is just in Blackboard at the bottom of our main class stuff. It's this one, West Virginia curve number table. So let me click on that and download it. Oh, it's displaying it, which I don't want. I want to download it. Maybe if I right-click and save as, save link as, that's what I want to do. Yes. All right. So we don't want to look at the data. We want to feed it into the computer. So this is going to be WMS demo HEC-1. Okay, so now if I go to that folder, WMS demo HEC-1, you can see it's not showing the file extensions, but it's just a text file that says different land uses that is corresponding to a color number. And the color number is, remember, what we get from National Land Cover Database. And then this is the equivalent curve number that would exist for soil type A, soil type B, soil type C, and D. So this is what it's going to read once it gets the land use and soil type out of the National Land Cover and the SURGO. So we're going to use that today. And in the handout, I mentioned that we're interested in a mixed rural and urban watershed in Morgantown. And the reason why it's significant that this would be a mixed watershed is, we can sort of spitball it a little bit for rural watersheds. If you're familiar with one rural watershed in this area, you can kind of extrapolate the curve number from one rural watershed to the next, because many of them have very similar soil types and very similar land covers. But then when you have a mixture of commercial, residential, and undeveloped spaces, all bets are off. And so you really do need to calculate a curve number kind of fresh. And so that would be the case in this region that we're going to look at in Morgantown today, because it's got part of the watershed includes the airport, part of it includes the city, and some of it's just raw undeveloped land. So we really want to have an accurate curve number, because these watershed models are really non-linearly sensitive to curve number. All right, so if you haven't already, open up the wizard and let's create a project file in case things crash and we need to come back. So put it in a new folder. I'm going to call this Morgantown. All right. And we'll save that. And so defining the boundary. I just noticed something today for the first time about this virtual Earth map locator. And what I noticed is that you can resize this window and that will affect the project boundaries. And so like if you just need a little bit more vertical height, like I did when I was just starting with Morgantown, first of all, maybe I'll illustrate directly. Morgantown, West Virginia. All right, so the watershed that we want discharges here. So this stream is going to be what we're trying to get. It's the West Run. Now obviously I'm not zoomed at an appropriate level right now, because if the stream on the picture continues off the screen, you haven't got the whole watershed. So, I mean, that's thing one. So let me zoom out a little bit more. Okay, out. Okay. When I delineated it earlier, this is zoomed in too much here. What you can do is basically drag this down, and then you'll get a little bit more area. You know, like the zoom level is kind of abrupt. Like when you say zoom out, it zooms out a lot. So now I've got lots of extra data. And so if I can see here's, I think, the northern boundary of my watershed. So you can maybe fine tune it a little bit just by adjusting the height and width of the window. Okay, so I think I've got the entirety of the watershed here, and I'll leave it for a moment just in case you want to look at some of the features and make sure that we've got the whole thing. So here's the stream that discharges. We want to know the watershed just before it dumps into the Monongahela River. We don't want to have the Monongahela River itself, but we just want the west run. All right, so click OK, and then the data that we're going to get using the web services includes the elevation. So we'll turn on, let me make this a bit wider, the world elevation. So it's already ticked, worldwide elevation data. I want to get NLCD 2011, National Land Cover Database 2011. And honestly, I'm not sure why Aquaveo haven't gotten the updated version of that, because I believe they do a fresh snapshot of all the land uses in the United States every 5 years. The government does, but that doesn't seem to have been integrated into the program yet. Maybe I'll send them an email and ask why. Because especially in places that have a lot of development, 5 years you can have new neighborhoods, and that can really adjust how much of a watershed is urbanized. Okay, so we want elevation, National Land Cover Database, and then scrolling down, we're also going to get this Surgo soil type shapefile. Now, as far out as I'm zoomed in right now, it's probably going to suggest like a 59-meter resolution, and that's a little bit too coarse. And so this is the first time where I'm maybe going to override its initial suggestion and suggest a different different zoom level. So let me click download, and let's see what it suggests for the elevation. Oh, okay. It's saying 29.4. When I did this earlier, it was saying 58.9. And I think that's probably just too coarse. And so I overrode that, and I put it at 29.4. And things still downloaded quickly enough. Topaz still was relatively quick. And you're always free to do that. The only limitations are time and space on your hard drive. So I probably won't take it to the 14.7. I'm going to leave it at 29.4, but I'm just curious, did any of you get prompted to do the 59 resolution? A couple? All right. If you went with it, that's okay. No need to start over, but of course you can start over and you'll still have your zoom level defined, which maybe at this point is the biggest investment of effort. So starting over with this button on the left here isn't too bad of a deal. All right, so click OK. Download data from web. It continues. Now it's asking me what cell size I want for the land cover database. By default, it's suggesting 20, and that's fine. That's all the resolution it's got. So we can go up from that, but we can't go down. Okay, OK. And then the longest one is getting the Surgo soil database. And since we're on the border of counties in our project area, it's going to have downloaded 2 separate counties. So I'm going to close this for now, and let's trigger these on and off. So it's a little bit clumsy in knowing which is the right county's soil data to get. I don't know what county Morgantown's in, but this is the soil data we need. And so we can tell that this is our project area, and this other one isn't needed. So I'm going to just delete this out of our project. So over here, take the one that you don't want and right-click on the words for it and delete. So again, in the Project Explorer is the list of all of our coverages and grids and GIS data. So we can kind of reduce how much is going on in the project by right-click on the soil data we don't want and delete it. And the one we don't want is 77. The one we do want is 611. Okay, so delete 77, it's gone. Okay, so any questions so far? We've got 3 things we've loaded into the Project Explorer. Our elevation data, the land cover, and the soil type. Okay, so opening back up the, well, maybe I'm going to turn off this soil type data for now just because I don't want to see it. And I'm going to turn off the land cover picture because I don't necessarily want to see that, or the heat map. Because remember, the next phase here is I'm going to run topaz and have it delineate the watershed. So back into the wizard, I want to compute flow directions and accumulation. I'm setting it at 5 acres right now, which is probably a little too low. This watershed is 9 square miles approximately. So, I mean, just to illustrate, if I go with it at 5 acres for the flow accumulation threshold, I'm going to see lots of blue. Okay, so maybe things are getting a bit cluttered at this point, so if I move to 12, that's still maybe more than I necessarily have to see. 20. Here's the main branch of the stream, and this, before it discharges into the river, is what we're going to be delineating. So I can definitely see that. Maybe I'll just take it to 25. And this is just a matter of personal preference. You know, what threshold you put here is not going to change the simulation itself. It's not going to change your peak runoff. It's not going to change the volume of water that is flowing out of here. It's just visually how far into the watershed do you want these flow accumulation cells to show up. Okay, before I create the outlet point, I guess it would probably be advisable for me to turn on a map and just make sure we've got the right stream. Even though I'm pretty confident this is the one, let's fire up the world street map and make sure that we're on the same page with this stream. Okay, so here's the river, and I'm going to click on the pixel for my outlet. I don't want it to be in the river. Things can get screwy if you put your outlet in the river. So I'm going to do it a couple of pixels upstream of where that happens. So back to the wizard, and our outlet should go here. All right. And delineate, and with any luck it's going to tell us we've got a watershed about 8.9 square miles. It's reporting it in acres right now. I think I can change the units that are displayed, but it won't update it unless I redelineate. So I'm not going to bother. Maybe just to check, there's 640 acres in a square mile, if I'm not mistaken. So 5693 divided by 640, yep, 8.89 square miles.
Is there like a number, like say we were doing this for like a property we were going to develop, is there a number that would be like a number you could see like where the water is actually going to be? Like normally, like you use whatever, 25 acres. If we just wanted to see like typically this is where the water would it be appropriate to use like a lower number to see that? Or
yeah, just to give you an idea, I live on the border of a watershed where the stream is ephemeral. Like on a rainy day, there will be flowing water. On a dry day, there's nothing there.
Right.
And the contributing area upstream of that is 7 acres.
Okay.
So, but you got to keep in mind it's steep, it's rural, so if it's an urban watershed, less than 7 acres maybe would give you flow.
Okay.
But, I mean, that's what I've noticed is 7 acres is kind of the border between an ephemeral and a stream that has water in it. And it's also going to be, you know, what kind of groundwater flow is going into the watershed. So there's really a lot that can vary. Okay, so is everybody with me so far? Do I need to pass by and troubleshoot any issues that have come up? We've got a watershed with area. We know the basin slope, the maximum flow distance. In the Project Explorer, we've got this soil data. Look at all those polygons. There's so much information there. Each one of them has a different hydrologic soil group. Like if you click on this identify tool and you've got the soil stuff going, you can click on one of those polygons and it'll tell you some information about it. Like there's an abbreviation for the soil type that it is, but we don't yet see the hydrologic soil group like A, B, C, D. We do want that information. So when we downloaded these polygons, let me go to this folder where the Surgo data is. Surgo is the high resolution soil type data. And if you open up that folder, there's all these different databases and shape files. So the shape file is kind of where the lines are, but where the line isn't necessarily all of the data that you need. We need to know the hydrologic soil group associated with each of those polygons. And so right now, by default, it hasn't joined together these shapes with all of the databases that there are. And so let's close this identify tool. If you right-click on the soil type shapefile, we're going to join NRCS data. So by doing that, what you're saying is you're linking together the soil texture and hydrologic soil group. We only need the hydrologic soil group, but there are some other models that would use the soil texture, or other calculations rather. And you'll notice this fill blank values option. Occasionally they don't have the data for a certain polygon. And so what you have the opportunity here is to fill it in with an assumption if the data is blank. Now our particular watershed that we're looking at here, I went through it before and I don't think there are any undefined polygons. There was in the demo on Friday. There were a couple of polygons that if we hadn't told it an assumption, then it just would have excluded them from calculating the curve number. And so unless you know otherwise, it's best to be relatively conservative, and soil group D is as conservative as you can get. You're saying if we don't have the data, let's just assume it's a plastic clay soil that is really poor at infiltrating water. And then what that will do is that'll increase your peak runoff, and then any infrastructure you've sized like culverts or bridges will be at the very least big enough. So let's have these 3 boxes ticked: fill blank values, join soil texture, join hydrologic soil group. Okay, click OK. And now it's linking together the database files with the polygons, so that I think if we use this identify tool again and we click on some shape, we get a more lengthy report that includes the hydrologic soil group. So you can see it's got the letter C there. Previously, before we joined the NRCS data, it didn't have that hydrologic soil group defined yet. So now all of these polygons in the watershed, we can know, okay, here's soil group A. I wonder what they've got at the airport. Soil group D. I don't know if that was a natural D. I think it, or if it was overwritten from our assumption, but it looks like with all the rest of this being blank, that might have been written. All right, so we've got these soil data polygons as a GIS file. We have to put them in something called a coverage. So you'll notice right now the only coverage we have is the drainage coverage. And we want to create a new coverage, the soil type coverage. And so right click on the word coverage with your mouse. So take the cursor over into the Project Explorer. Right click on coverage, new coverage, and we're going to do soil type coverage. Okay, so that just creates a new area for us to copy in data. I'm going to pause for a moment here. So you can always turn off these. Like if you're trying to see something, you can turn it off and turn it back on later if you want. But you know, the density of those soil polygons would make it pretty tricky to see anything else on the map. So I'm going to turn that off and go back into the drainage coverage. You see that when you switch from the drainage to the soil type coverage, you see different things. The watershed boundaries kind of become grayed out when you're in the soil type coverage. And right now there really isn't anything in the soil type coverage. And I can turn off the street map again. I don't need that anymore, so I don't necessarily have to display that. Okay, so what we're going to do is this next step. Remember the soil type shapefile. We joined NRCS data. Now we're going to select the polygons that we want to copy into the soil type coverage. So okay, the 2D grid module, yeah. So in the 2D grid module, GIS module, okay. Go into the GIS module and do the Select Shapes tool, and then click a box that surrounds the entirety of the watershed, because what we want to do is we want to select all of the polygons that run through the watershed. So if I zoom out, you can see by doing that, it doesn't have all of the polygons in the county. It just has any of the polygons that runs through that area that was in the selected window, which includes the river, because the river is a single polygon that goes through our watershed and much further beyond. Okay, so again, if you missed that selection, what we got to do is figure out, here's our watershed. Okay, turn on the shapefile, and here in the GIS module, click the Select Shapes tool and draw a rectangle that encloses the watershed so that we've selected all of those polygons. And now we're going to say in the mapping drop-down box, shapes to feature objects. Because right now, these are just shapes in the GIS data, but we want them to have more significance in our model than that. We want to say that these particular shapes are important for calculating the curve number. And so this mapping step is where we do that. We're going to paste these ones that we've selected into the soil type coverage. Okay, so mapping shapes to feature objects, and then we tell it that the things that are selected should go into the soil type coverage, and it's going to be coming from this GIS shapefile. Okay, so that was the default, and it's right. Next. Now, it's going to do its best to try and match up data in the GIS file with attributes that can exist in a soil type coverage. And the one that's most important for us is this hide group data that was in the shape files. It's going to map that to SCS soil type. So make sure that it has that mapping set, which is correct. The rest of these aren't significant for what we're going to be doing, but they can be important for other soil calculators and other models. The most important one for us is just making sure that it knows this hide group data should be mapped into the SCS soil type for the soil type coverage. Okay, so click Next and Finish. Okay, so now if we turn off the GIS data, we can see that we've just got those selected shape files in the soil type coverage. So now if I switch to the drainage coverage, the soil type ones are in the background. I can turn them off if it makes it easier to see things I'm trying to look at. So on, we can see them kind of in the background in our watershed. Part of the reason why I like to turn down the density of the flow accumulation cells is that if I had left it at 1 acre, there would be these black lines everywhere in the watershed. You know, there'd be so much flow accumulation cell, you really wouldn't be able to see anything else. So it's just mainly a display preference issue. All right, so what we have now is this soil type coverage, our drainage coverage, and the drainage coverage is what the basin shape is located in. And then we still have this land cover grid. That is the picture that has different colors that says, you know, if I want to look at those pictures, it says where are the urban areas and where are the rural areas. And so over here on the west side of our watershed, which we know is the urban part of it, you can see that we've got red colors, and then there's these undeveloped zones or residential areas that have different colors, and it's going to be matching up those different colors to these rows. And so, for example, I think that the developed high intensity 24 is a red color, and so it's going to look at what is it's going to combine together any place there is an overlapping land cover cell with this soil type data. So it's going to do like a calculation of, like, in each one of these soil type shapes, what's the percentage of each kind of land use. And so it's going to come up with a weighted average of the curve number for each polygon and then for the overall watershed as a whole. Okay, so before I move on to actually calculating the curve number, is there any questions so far? All right, I'm going to turn this off. I don't need it. I don't need to see this. All right, so now I think we need to be in the hydrologic modeling module. We were just previous to that in the GIS module where we did this mapping shapes to feature objects. Now switch into the hydrologic modeling module, and the calculator we're going to do is compute GIS attributes. Okay, so it's going to calculate the SCS curve number, and you'll notice it says it's using the soil type coverage for soil type. It's using a grid for land use, and the only grid we've got is this land cover database grid. And then we need to import the map of the table, and so that's the text file that we've downloaded from Blackboard, WV curve number. Okay, once we've imported that, you can see it's just that text data, so it's going to use all of this. And as soon as you click OK, it starts calculating the curve number inside of the watershed. It'll prompt you that here's this text file that has a report, and it's just saved it in a temporary folder, so that if you want to have that available, you're going to need to save it somewhere else. But we're opening it with a notepad when we click OK, and it looks like 69.2 is what I've got for my watershed. Did anybody else get a similar curve number for yours? So I see the nodding heads. That's good. The repeatability is really important. Hydrology is, and sometimes it's as much an art as a science, and people can get a little uncomfortable with the idea that you're just using your judgment to assign things. And so anytime you've got a repeatable, quantifiable method that's based on government data, that really enhances the authoritative nature of your watershed model. So here we can say with some confidence and justification that our curve number for this watershed is 69.2. which is pretty low considering how much urban area it's got. So if we look at the report, like, why is it so low? Well, we have some type A soils in the watershed. You see, it would be pretty uncommon to see so much type A soil in Huntington, at least. Do you have a question?
Yeah, are those units in acres? Because it says square miles, but
Yeah.
mine is like 0.448 square miles.
Yeah, that would be a lot of square miles.
So yeah, this isn't miles. It's acres. Does anybody's report actually say acres rather than miles? I switched my units partway through. What I did was I switched it to miles after it actually calculated the areas. So it's probably the discrepancies related to that. In the end, did I close my soil type report? In the end, since it's just a weighted average, even if it was assuming miles rather than acres, it's going to give you the same curve number in the end. All right, so we've got curve number defined. That's on the display. Let me move this watershed symbol out of the way if I can. Select the watershed. With these colors being screwed up, it's really hard for me to pick at things. Well, by the way, there's a couple of interesting features I haven't showed you before. If you're in here at the drainage module, so go into the drainage module, you see this little flow path indicator. If you click on the map, it will show you what path water would take to get to the outlet. So it's kind of tracing the flow directions. So that's kind of interesting. And if you select the basin, over on the right-hand side, it will give you all of the properties that have been calculated so far, like the area. This is reporting it in acres, the curve number. I probably shouldn't have changed the units over like I did. Let me change it back and see if that will rectify things. Back to acres. Yeah, all right. 5693 acres rather than saying square miles. All right, so HEC-1. We've just got 7 minutes remaining. When we're in the hydrologic modeling module, in the drop-down box where we could have chose NSS or rational or TR55, you'll notice that HEC-1 is one of the options. HEC stands for Hydrologic Engineering Center, I think. U.S. Army Corps of Engineers people probably know. Is it HEC, Hydrologic Engineering Center?
We're not in hydrology, neither one of us. So.
All right. Well, once you're in HEC-1, do the Select Basin tool and double-click, and we'll open up these HEC-1 parameters. If you click on basin data, you'll notice that it's got the watershed area. Here it's saying 8.89 miles, so that's correct based on what I already know. I can cancel that. Output control, we don't need to be involved with this. One of the things I'll have to remind you of is I mentioned that some of these watershed models are really old and they were developed in the 70s. And WMS is acting as a preprocessor where it's translating the data that we have on screen into a text file that's going to be run by the model itself. So you see all these abbreviations down in this white window. These are related to the parameters of the watershed. So you can see here it says BA 8.8954. That's the basin area in miles. And then you see LS. And the second field in the LS row is the curve number. So it's got the name of the basin, 1B. We're going to fill in information that makes this HEC-1 file output much larger and is preparing it for the simulation. So click on precipitation. We're going to do basin average precipitation. And what basin average is saying is we assume that it rains the same depth everywhere over our watershed. You don't have to do that. You could take other approaches like assign multiple gauges on the map and have them weighted accordingly. But we're just going to assume that it rains the same depth everywhere. Get precip from web, click on that button, and it's connecting to the precipitation data frequency server. And let's take a look at the 10-year recurrence interval. So tell it 10-year, and then for this latitude and longitude, when you click on get data, it pulls the precipitation data frequency server and says it's going to be 3.459 inches is the rainfall depth. So click OK, and it's copied that here into the average precipitation. We're not done yet, because we also have to define the series. Define the series is where you translate a depth to a distribution over time. In other words, it needs to know, is this a 24-hour storm, a 6-hour storm, type 1, type 2? Basically, how are we translating the amount to a distribution over time? So when you click on define series, the option we're going to choose for this model, scroll down to type 2 24-hour. And then the curve that comes up on the screen is that shape we've seen before. It's the fact that it's saying on average a type 2 storm would have a relatively slow beginning, it would taper, it would come to this period of maximum intensity where the distribution, the amount, is changing a lot, and then it would slow down a bit. There's no single storm that would look exactly like this, but on average, across thousands and thousands of storms, this might be a typical behavior for type 2. And so what it's doing is it is translating that shape into different time units. So you can see in minutes, every 6 minutes it's finding out what percentage of the storm has occurred up to a certain point. So it's going to copy this and the depth down into this HEC-1 file output. When I click OK, now that's suddenly a lot longer than it was before, because it's saying how much of the rain occurs at what time in the storm. So it's going to go step by step by step, different times, and analyze how much rainfall is there, how much was there before, how wet is the watershed, compare that to the curve number, calculate the runoff, the rainfall excess. So it's going to be pretty sophisticated because of this time resolution. Loss method, it's going to use the curve number to calculate the loss. Okay, we don't have to do anything there. The last thing is unit hydrograph method. We're going to use an SCS dimensionless unit hydrograph and compute the parameters from basin data. So choose lag time SCS method, and you'll notice it's calculating the lag time based on the watershed length, this curve number that was calculated, and the slope, which is known based on the digital elevation model. It's saying 1.98 hours is the lag time, and once that's calculated, it turns it into the curve number. Excuse me, it takes all the information like curve number, slope, and the length of the stream to calculate the lag time. So click OK, and it's copied that lag time as well into this file. So you can click on Done, because we've built a complete simulation file, and now in the HEC-1 dropdown, do Run Simulation. And if you want to pick a specific location to save the output file, you can specify that. I'm just going to leave it in the default. Click OK. It's ended the solution, and there's a hydrograph that's on the screen. And if you double click on that, then it brings up the shape of the runoff here. So it has a peak of 1,044 CFS. And you can see the time to peak, assuming that the storm event begins at time 0. So this is where we'll pick up on Wednesday. We're going to continue working with HEC-1. I want to show you a few other tools that are available to us. But my strong suggestion is to practice this, because familiarity comes from just repeating the process a few times. And so that's it for today. Let me know if you have any questions as you go through it, and I'll see you on Wednesday.